So the first two definitions are relative maximum and relative minimum. What does it mean to be a relative? I'm assuming you understand what a max and a min mean. So what does it mean to be a maximum value? Alex?
Like in a function where it goes down, like that little hump, the peak of the hump in the middle would be a relative maximum.
Okay, yeah. And so a relative minimum similar would be the lowest point. But by relative, what we mean is it's not the lowest or highest point overall. It's the lowest or highest point in the region that we're talking about. Pranay, you need one of those. Okay? So it's just relative to other points nearby, it's the highest value. So for a relative maximum, exactly as Alex explained, okay? In that function, how many relative maximums do we have? We have 2. So here and here, we have a relative maximum. And here, and here, we have relative minimums. Okay? But these are not the maximum value for the whole function because the function continues on. So in fact, there's no absolute maximum for the function, just as there's no absolute minimum for the function, but they are relative maximum. So it's relative to nearby points. The tallest point, or the highest point, and the lowest point. Sherry, that's for you. Okay? All right. And Piper, this is for you. So how could we find these points? What is happening at relative maximums and at relative minimums that would allow us to figure them out? Miles? The derivative is equal to 0. Okay? So if we have a relative maximum or a relative minimum, then the derivative is equal to 0. Oh, sorry, Liam. Okay, does that make sense to everybody? Now, the other thing that is happening with relative maximums is the slope on this side is different from the slope on this side. The slope on this side, is it positive or negative? Positive. And on this side? It's negative. So for a relative maximum, we're going to be increasing to the maximum and then decreasing. For a relative minimum, it's the opposite. We're going to be decreasing to the minimum and then increasing. So the increasing and decreasing pieces have to do with the sign of the derivative, which is the sign of the slope. Negative slope, like this, is a decreasing situation because we're traveling always from left to right and the y values are getting smaller. Okay? If we're traveling from left to right here, the y values are getting bigger, and so that's increasing. Okay? So on your definition under increasing and decreasing, is that the next ones that I have? Nope, I have the absolute maximums and absolute minimums. Okay, so under increasing, the y values are getting bigger. The slope is positive, and so the first derivative is positive. And for decreasing, it's the opposite. Okay, so I spoke to this already, but absolute max and absolute min, we're talking about the highest point over the entire domain of the graph. Okay, so it might be a restricted domain or it might not be, but the highest point for the entire domain is going to be your absolute maximum, and the lowest point for the entire domain will be your absolute minimum. And you don't always have one. So it depends on the function, it depends on the domain, and we will do lots of examples today so you can see that. I was going to say something there, but I can't remember what it is. Anyways, when we talk about the maximum and minimum values, what is it that we are specifically referring to? The biggest value of the graph, we are asking you to find but which one, the x or the y? It's the y value, okay? And the location of those maximums and minimums, that's the x value. Okay? So a question will say find the maximum value, find the relative maximum of such and such a function. So you can find it, and then the x value is where it's located. So it's located at x equals 3, the maximum value is 22. Okay? Now another word for absolute max and min is global max and min. Okay, so global just meaning for the whole thing. And for relative max and min, we can say local. So you might see them to say local max and min when they're talking about relative max and min, because it just means in the local area it's the biggest value, or in the local area it's the smallest value. Any questions so far about those definitions? Okay. Now, notice down below, I have a couple of points. At relative extrema, the graph changes direction from increasing to decreasing or vice versa. So we talked about that. And at relative extrema, the tangent line is either horizontal or the function could also be non-differentiable. So a cusp or a corner. At a cusp or a corner, you will have a maximum or a minimum, a local one at least. Okay? But you won't be able to set the first derivative equal to 0. So up here where we said the first derivative equals 0 or non-differentiable. Okay, so cusps or corners can also be local or absolute extrema. So those are the things that we're going to be looking for, okay? Now it's also important to note that not all critical numbers are going to give you extreme values. Okay? So not all critical numbers are going to give you extreme values. But we are going to look for critical numbers because that is where they will occur, if they occur. They will occur where the first derivative is equal to 0 or non-differentiable. But they will occur there, but they may not occur there. Okay? So that's why we did talk about critical numbers on Thursday. And I'll show you some examples of where we will have a critical number that is not an extreme value. So you'll see what we're talking about there. So you have to do a couple of different tests when you're looking for extreme values. Then the last point on that first page, relative extrema do not occur at the endpoints of a closed interval, but global extrema do. So here, for example, if I have a graph that looks like this, okay, I have two extreme values here. Okay. Anyone want to take a guess at what I've got? Where will my minimum value occur? Right here. This is a minimum value, and this is a global minimum because it's the smallest. the smallest y value over the whole domain. Okay? Now, I also have a maximum value that is both a local and a global maximum. And that is right here. So that is a local and global maximum. Okay? But we don't call this a local minimum. Okay? So because it's at the endpoint. So anything at the endpoint can be global. It's not necessarily. This is neither a maximum nor a minimum. Okay? But endpoints can be global maxes and mins, but they can't be local maxes and mins. This is local and global. It's local because it's increasing on the right and it's decreasing on the left. This is not local because it doesn't change direction from increasing to decreasing there. Okay? So at relative extrema, the function must change direction. But at global extrema, they don't have to. So here it doesn't change direction, but it is the lowest value for the whole domain. Questions about that? So we're really still kind of just defining what they mean. I should have. Okay. Oh, and I didn't write the function in. How about that? All right, so we're going to do an example. Another example here. And it is, you can write it in, f of x equals 4 minus 3x minus x squared. And what I want you to do is find the intervals on which f is increasing and decreasing. So I'm going to give you a moment to think about that on your own. So f prime of x is negative 3 minus 2x. And that equals 0 when negative 2x equals 3 or x equals negative 3 halves. So that is a critical value. Okay. So now the question is the function changing slope on either side of that critical value? Is the first derivative changing sign on either side of that critical value? So if we think about it as a number line, where here's negative 3 halves, what is the slope to the left? If I plug in a number to the left of negative 3 halves, give me a number to the left of negative 3 halves. Negative 1 would be right here. Negative 2 would work. So we plug negative 2 in here. I get negative 3 plus 4 is 1. So that's positive, right? And if I put a value over here in, like 0, I get negative 3 minus 0 is negative 3, so that's negative. So it's increasing on the left and decreasing on the right. Okay? Now, how can you write that in interval notation? You could write as a statement, you could say that it is increasing for x less than negative 3 halves. And it is decreasing for x greater than negative 3 halves. So as an interval, it is negative infinity to negative 3 halves. And here it's negative 3 halves to positive infinity. Okay? And I think your textbook favors interval notation rather than the statements. Yes, Alex?
Isn't it increasing when x is greater than negative 3 over 2?
So greater than negative 3 over 2 is here. And I'm saying that your first derivative is negative there.
Right.
Because I tested a value to the right, which was 0. I put 0 in here, and I got negative 3, so that was negative. So over here, it's increasing, and over here, it's decreasing. We okay with that? Yeah. Okay. Questions about that? Yeah. So if it is increasing on the right and decreasing on the left, what kind of extreme value is this? It's a maximum, right? Because it's increasing and then it's decreasing. So is negative 3/2 the maximum? No, it is where a local maximum occurs. So if we wanted to find the maximum value, what would we do? Plug it back into the original function. So we would want to know what is f of negative 3/2. So that was 4 minus 3 times negative 3/2 minus negative 3/2 squared. So we would have 4 plus 9/2 minus 9/4. So I'd have 16/4 plus 18/4 minus 9/4 is 25/4. So that's the maximum value of this function, and it occurs at negative 3/2, which is a local maximum, but also it's a critical x. This is the critical value. So now we found the critical point, negative 3/2, 25/4. But this is also a global maximum. How do I know it's a global maximum? It's an upside down parabola, and so I know that that's the only extreme value in the whole domain is at negative 3/2 and positive 25/4. Okay? So this point questions about that? Okay, so then we have, what else do I want to do here? The first derivative test for local extrema, which is essentially what we did there, but we're just going to formalize it here on the sheet. So it says if we have a function f of x, then we're going to find the critical points, point or points, by looking for, where do critical points occur? Where the derivative equals 0, or where the function is non-differentiable but still exists there. Continuous but non-differentiable, okay? So then we are checking to see so we're going to find the critical values. And then you're going to check the increasing, decreasing. Okay? And on the sheet it says, number 1, if the first derivative changes sign from positive to negative, what have you got? If you've got a maximum. So if you're going from increasing to decreasing, then you have a maximum. If it's going from a negative to a positive, then you have a minimum. Okay? And what if it doesn't change sign from a positive to a negative? What does it say there? F, the first derivative does not change sign from positive to negative, or from negative to positive. Yeah?
You have an increasing or decreasing function?
Yeah, it's quite possible, but the first derivative test there is kind of inconclusive. We need to check other things. Okay? So for 3, if it doesn't change sign, then it's inconclusive. So we'll have to look again. But here's an example of one that doesn't change sign. So we'll have a flattening right there, but it's increasing on the left and it's increasing on the right. So we don't have a local maximum in there. Okay? So that's an example of it. But we may not have that situation either. Another possibility is that we have something like this. Okay, and that will happen if we have very high powers of x. So negative x to the power of 10, for example, could look like that. And if we're not testing far enough out, it may show up that the sign's not changing when in fact it is changing there. So we have to just look a little bit more carefully if we're thinking that the sign is not changing. Think about how the graph actually would look. Okay. Questions for me? So it's inconclusive, but it typically means that you're going to have no extreme values. Okay, so just be aware of that. Everybody okay so far? All right, so the next example on this page says example 1. Clearly it's not example 1 because we've done some examples already, but it's an example 1 of using the first derivative test. Okay. So it has a part A and a part B. They are 2 different functions, so it's really 2 different examples. Find the critical points of the first function. Look for local and absolute extreme values. Identify the intervals on which f is increasing and decreasing, and then show a graph. Okay, I've made a mistake with this one here. It's not inconclusive. I was mixing it up with the second derivative test, which we'll talk about tomorrow. So if it doesn't change values, you have no relative extrema. And it looks like this situation here. Okay? So it flattens out and has a horizontal tangent, but it doesn't change sign, so you have no extreme values. Okay? So for this first example with the first derivative test, where f of x equals x cubed minus 12x minus 5, the first derivative is 3x squared minus 12. And that equals 0 where x equals plus or minus 2. So everybody's getting that, I'm seeing. Okay, so those are your critical values. And that was the first thing that you were supposed to do. Find the critical points. Now, those are the critical values. So the critical points occur at 2 and negative 2. So we want to plug 2 in here. And we get 8 minus 24 minus 5, which is minus 21. And when we plug negative 2 in here, we get negative 8 plus 24 minus 5, which is 11. Okay? Everybody okay with that? So did you get the points 2, negative 21, and negative 2, 11. Okay. Now at this stage, you know what this graph looks like. You should know. What does it look like? A cubic function has that S shape, okay? And it's a positive cubic, so in general the function is increasing or decreasing? Increasing in general, but we are going to have this little jag here. So at 2, I'm at negative 21 down here. And at negative 2, I'm at positive 11 here. Okay, and so obviously this has to be a maximum, and this has to be a minimum. Not drawn to scale, clearly. But are they local max only, or are they both local and global? Because clearly they're local, right? This is the biggest point on either side. This is the local min. It's the smallest point on either side. But are they global max and min? No, why not, Pranay?
Because the right and the left of the graph go to negative.
Right, because of this arrow here, there is no maximum absolute, and there is no absolute minimum because these arms go on forever up and down. Okay? Questions about that? Yeah?
When you test a point, like say you weren't graphing it, when you test a point, do you dig into the derivative or?
And what are you testing it for? To find increasing or decreasing? Yeah. To find increasing or decreasing, we want to go into the derivative. So we didn't do that here because we knew what the shape of that graph was, but you certainly could. So you would put in your number line, your negative 2, your positive 2, and yeah, now you're going to test values into the first derivative. So if I put negative 3 into the first derivative, I will get 9 times 3 is 27 minus 12, that's positive. Then if I put 0 in, I'll get negative. And if I put positive 3 in, I will get 27 minus 12. That's also positive. So yeah, we tested into the first derivative. And notice that that mirrors the shape of my graph. Increasing here, so positive slope. Decreasing here, negative slope. And increasing here, positive slope again. So the question did ask for the intervals for increasing. And so this is what we would write if we were writing it in interval. Well, let's do it in both. We could do number line. We can do x less than negative 2 or x greater than 2. That's where we're increasing. Or to show it in interval notation, we say negative infinity to negative 2 union 2 to infinity. Okay? So it means this or this. That's where we're going to find our x values where we're increasing in the function. So this union just means the same as or. And you could write or instead of the capital, or it's not a capital U, it's just it's a U shape. So you could also just write or if you'd rather. And then decreasing is between negative 2 and 2. So this is as a statement, and this is in interval notation. And I didn't record any of that. Questions about that? So now the next one looks kind of nasty, right? And it is, it's a little harder. Yeah. Okay.
It's a horizontal line. Does that count?
Oh. That's a good question.
Yeah. Has a maximum.
Or you could say that all values are both maximums and minimums.
Yes.
Some more horizontal lines over there.
Yeah.
It's pretty advanced stuff. Watch out.
Okay, so why must it have both? Why must it have both in the interval? It's closed, and so we are looking at not only the critical values, but also the endpoints, okay? And so the endpoints are going to define for us possible absolute maxes and mins, as well as any critical. I will come around and check on how you're doing, and then we will discuss it right at the end. And we won't quite get finished today, but that's okay. We'll finish it quickly tomorrow, and then you'll have time to practice tomorrow. And if you're going to find the maximum value, that means you've got to find the y values that go along with these. It's a little bit trickier. Okay, that's what you've got, and I won't report that. I will report that. Okay? Yeah. Oh, right, yeah. What are we getting for the two critical values here? Hopefully. It's a long recording, so hopefully it'll go without too much trouble. What are the two critical values? Did we find them yet? 0 and 3/4. It should be 3/4. Right? If we take the first derivative, yeah, can you give me a fraction for that one? What'd you get? Oh, no, I got -1 as the minimum. Yeah. Oh, wait, I put it in. Oh, you know what? I wrote the endpoint wrong, that's why. Did I put the endpoints 0 and 3? I did. And on my sheet I had -1. The endpoints here were -1 and 3. On my sheet I had -1 and 3/2. So that's probably why. Okay. Okay. So you're like correct. All right, I will do your mark, right? Oh, that's not even. Ah, good job. Pull it out. Oh, hey. I can change it if you want me to.
I'll take that. I'm happy. Nice. I'm okay with it. 81? I'm not good with it. I want to 5%. I know. I don't know.
Wait, you're all I want to
All right. So when we plug 0 in, obviously we get 0, so that was a nice gimme. When I plug 3/4 in, you can do a decimal, but you should be able to do a fraction. 3 times 3/4 squared minus 4 times 3/4 cubed is 3 times 9/16. 3 times 9/16 minus 4 times 27/64. So I get 27 over 16 minus, the 4 divides out there, minus, oh, that's not right. I'm getting 27 over 16 again. Do I get 0 for 3/4? No, I do not. All right, what did I do? I'm putting it into the derivative. Thank you. So that would be bad. I don't want to do that. Of course I get 0 when I put it into the derivative because that's, I just found the critical values of the derivative. So it's x cubed minus x to the power of 4. So it's 3/4 cubed minus 3/4 to the power of 4. So that is 27 over 64 minus 81 over 256. And when I do this, and you can do it, but we're running out of time, you get a common denominator, and it should be 27 over 256. Watch out for that. F of -1 is -2, and F of 3 is, what is it?
-54.
So your maximum is here, and your minimum is here. Okay? Everybody okay with that? So tomorrow, we're going to have silent reading. You're going to get to look at your term exams, but not keep them. And then you're going to get to work on this stuff. Okay? And we got a few more things to talk about here. Like, two things.
Yeah, no, you'll be playing Joel.
Who wasn't here today? Curtis? See you tomorrow.
Yeah, no, like the piece in here. So for every couple different features.
Peter, I had your thing all this time. I just had it with my wrong class, so I'll get it for you.
Don't lynch me! I'm serious. Tracy, you're serious. Don't lynch me. Usually tip like not like. I know
It's 6x cubed plus 1x squared.
Really?
I'm trying to move it.
Oh my god. I think that was the episode where he's like, if I was so on two bullets, and I was having it. I just like, cause I was gonna like, was like best bullets of microscope versus toys. And then that came up and I died. I actually died.
That was so free.
When he was like, no, God, no, please, no.
I think it was
all over the right? I was like, and then I saw it like all over the
This is the moment. We'll finally damage it.
Oh, that's happening.
I'm living.
Yeah, he changes so much.
I think all of them, like,
The only person who doesn't really change in the first episode is like Kevin.
Even next to me. Yeah. I wrote down for you. Well, if you wanted just one, right? Just like that. Got too long.
Look, Kevin, you could have just said, like, not center. I didn't see that.
You were saying this is
I didn't see that. I didn't like it. And when we're done,
no, that's how you do the first step, and then you go to the other part.
yeah. And I was like, sure. No. I have it. Yeah, I do want it. Oh, I thought you did. No. I do need it. I know.
And have a swag. Bring back.
You said bring back the hat.
how do you just,
Okay, with your groups, can you look at your homework, please, and see if you have any questions from it? Open it up. You had page 204. No, page 209 in your textbook and page 357 from your the handout. Okay, so have a look at that, please.
Then it's like X cubed to X plus 1.
University during grade 12.
How did you do that?
The application deadline is this Friday,
This
April
is x to the
22nd.
power of 3 plus
Billy
3x
Elliott,
to the
money
power
and
of 2.
application submission for the Billy Elliott trip to Vancouver.
You mean x to the power of 3.
With payment and signed form.
So, yeah.
Knitting Club comes from C106 at lunch today to learn how to knit. No supplies are needed. Come and learn this community-based project and there's zero hours of your grad transition. The 4% Club meets every Monday at lunch in room E202. Model UN and Debate Club. There's a Model UN and Debate Club meeting every Monday at lunch in room E204. Everyone is welcome. Grad clothing. Grad students don't miss ordering out grad clothing. You can still fit in an order. It just has to be in by Friday, April 22nd. That's this year. Track and field. Attention to remain laser bar. Track and field fees must be paid by this Wednesday, April 20th, 2015. Bring your fees to Ms. French as soon as possible. Golf team. Would the volunteers please come to the office to see Mr. Nelson right away? So that's the names are good. Ellie Green, Jiraiya Morris-Worthy, Maddie Ho, Shirin Anjawala, and Grace Kwan. Alright, the deal of the day at the cage. Come on to the cage at Let's Say and buy a mini chocolate croissant for only 50 cents, receiving 25 cents at the wave. Dodgeball, come to the teacher versus student day this Wednesday at lunch. So whose teams will be cheering you on? Alright, physics students, this will be an announcement for all students personally, or taking on the current if it's 11 or 12 business school or Mr. Carell. The Playland trip will take place on Tuesday, May 3rd this year. The cost is $45 to $50. If you're interested, come on for information meeting in Mr. Carell's room, and that's D101 at 11 tomorrow. Tuesday for details and permission forms. Math Fest 2016, everyone who's signed up will be playing today. Math takes place in room E108, that's your right room.
So basically you do what's in here first. You do what's in here first. Look at this. And then use this to times this. So I mean this lower part. Yes.
From 5:30 to 7 o'clock in the library. Alright, so thank you for your absence. Have a great day, everybody.
Okay, so you're with your group, you're trying to figure out if you had any questions, and I'm going to take them up in 2 minutes. So you have 2 minutes. Figure out if you have any questions from your homework that you would like me to do. Okay, any questions from the, who do I have here? From page 209 or from page 357? Anybody? Yeah, Matt? Which one? The worksheet and page, so which one is it? Number 19 on the worksheet. Can I have a look at yours? Okay, which one? 19. 3x minus 2y cubed. All right, so on the worksheet we've got 3x minus 2y cubed. How are we going to manage this one? Brandon?
You put it in 3 parts.
Yeah, so it's 3x minus 2y times 3x minus 2y times 3x minus 2y. Okay? And what we do here is we just do a pair at a time. So we're just going to multiply these guys first, and we'll leave that one alone for now. Okay, so when we do that, we'll go 3x times 3x is 9x squared. 3x minus 2y is minus 6xy. And then 3x minus 2y is minus 6xy. And minus 2y times minus 2y is plus 4y squared. Are we okay with that? Okay? Now I want to multiply this onto this, but before I do that, I'm going to combine those like terms, because having one less term means two fewer operations that I have to do. So this simplifies to be 9x squared minus 12xy plus 4y squared onto 3x minus 2y. Okay? And now we want to hit this with everything like that. Okay, so we want to make sure we hit those 6 multiplications. So the 9x squared has to multiply the 3x, has to multiply the minus 2y, then the minus 12xy has to hit the 3x, and the minus 2y, and then the 4y squared has to hit the 3x, and then the minus 2y. So there's a lot of multiplications, and there's a lot of places we can make a small mistake, but essentially that's all you're doing. So we first multiplied these two, simplified, and then took that trinomial, multiplied that binomial. Now we want to simplify. I've got, these are both x squared y, and these are both xy squared, so those can combine. 27x cubed minus 54x squared y, and then plus 36 xy squared minus 8y. Does that help?
Yeah.
Okay. Questions for me about that? Okay, so the cubing ones are tricky because you're going to do a pair at a time and then bring in the other one, the third one at the end.
Like, so power is like 4.
Power of 4, you do it the same way. If I had a power of 4, or any even power, I think what I would do is multiply these together and multiply these together and then multiply those two together. Okay? So here you do your FOIL, here you do your FOIL, and then you have a trie times a trie. Okay? So, yeah, it gets more complicated, but it's exactly the same thing that you just keep repeating. Multiply, add like terms, multiply, add like terms. Okay? Okay, I wanted to do an example of a cube, so that's nice that Matt asked that question. Any other questions from the homework? All right. So the squared was one okay. And what about binomial times trinomial? Is that okay? Nobody have problems with that? All right, so let us try. I'm going to do 3 problems with you today, and then we'll do some board work, and then you'll have some practice. It's more of the same, just a little bit harder. Okay? Remember, I'm here at lunchtime today, and remember, you have a notebook quiz tomorrow, so you want to get caught up on your homework for tomorrow, because I'll be looking at everything we've done in 5.1 and 5.2. Okay, open up to you.